And thanks a lot for the introduction, and also thank you for inviting me here. It's my great pleasure to be here. And today I'm going to talk about humanoid robot learning. So the title is Beyond Imitation, Executable, Correctable, and Adaptable Skills for Humanoid Robots. So each of these three words, they are not really arbitrary things. So hopefully by the end of the talk, you can understand why I just put it here in this title. So yeah, so let me start. Before I talk about the technical content, I want to be precise about what I mean by skill. So because this word has been widely used in the community for different meanings. So a robot skill in this talk specifically is a closed-loop sensory motor policy that achieves a goal under some real-world variability. So across environments and disturbances, it has never been seen before. So here, three things matter in this definition. Closed loop means you have to respond to what happened in the real world, and goal means you want to achieve some tasks. While for real world variability, including environments, disturbances, changes, it means some kind of generalizability. Okay, so it's not just like replaying something you have already known, but really to understand how to adapt and react to new changes. So in a typical humanoid stacks, so perception will feed into some planner, and then some task intent goals or references will be generated, and then the skill will be in charge of executing, correcting, adapting to the real world, and finally you get the real world physical robot behaviors. So in this talk, I'm not going to talk about VLA, WAM, these kind of things, but more specifically focusing on this skill execution. So like something shown here, okay? Uh, yeah, so when we talk about this kind of skill learning, a natural question is, where does this kind of structure behind these policies come from, since it has a lot of requirements, right? You have to move your whole body coherently, you have to react properly to the real world, you need to understand which behaviors that are really useful for achieving tasks. Well, especially for kind of task achievement and also for whole body coordination, we know there's a natural kind of source for this kind of structure prior, which can scale up easily, which is human motion. So it provides us whole body coordination, diversity, and structures. So and also it's more scalable than robot data itself. So that's why we want to leverage human prior to achieving robot skills. However, human data is not really robot-ready skills. So there's a huge gap, and this is also the central tension for today's talk. So between human motion and real humanoid skills, there are several gaps. Embodiment gap, there are different body, different sensor, different kind of kinematic chains. And for task gaps, for human motion, you're just mimicking or doing something human-like, but whether it can achieve certain tasks, there is no answer. And also reality gap. Even if you have learned all the perfect robot skills in a simulator, it doesn't mean you can naturally transfer to real world to achieve tasks. So for the rest of the talk, I'm going to talk about these gaps one by one, okay? So this will be the organizing equation for this talk. So we kind of define real world skills as some broad behavior priors plus structure deviations and also plus grounded dynamics. So this three components specifically tackles the three gaps I just mentioned. You have to generalize or you have to establish a broad human-like robot behavior priors so that you can learn from human motion, but embody those things onto real robots. And you have to learn how to structurally deviate from these priors, achieving various of tasks. And finally, you have to ground your behaviors to real-world dynamics so that you can close the sim and real gap. So the next three sections will basically talk about this component one by one. I will start from the broad behavior priors. The key is to kind of establish a prior or motion foundation so that it can cover diverse and robot executable behaviors. Okay, so here is a kind of practical version of the embodiment gap. You have the mocap, you have the motion estimation from image or videos, but right-hand side, you have the robot motions. So you do see there is quite a pretty huge difference, and we need a compiler which can help us to compile those human motions to robot actions. Okay, so the real kind of challenge is how to make this happen. So the first contribution I will talk about is this compilation problem. So the goal in this work called track any motion under any disturbances is to kind of close this gap by learning to kind of convert human motion into diverse and robust robot behaviors. Okay, so this is a work presented in the past ICRA 2026. Here you see we want this rubber prior or rubber motions to be both diverse and also robust to external disturbances. Well, naturally, these two problems has been kind of considered in a single paradigm in the previous works. However, we find it shouldn't be the cases because for diversity and robustness, most of the time they kind of conflict with each other. So the key design in this work is trying to decouple and separately learn expressivity and robustness. So most prior works trains a single policy that is both expressive, and robust. We argue this is probably not the most ideal thing. We should learn these two properties separately. So we just decouple them. We have any tracker which can track this kind of human motions, arbitrary human motions. While on the same hand, at the same hand side, we'll also have any adapter which can kind of modulate this any tracker's behaviors to make sure it can cope with real world disturbances. Okay. So to be more specific, any tracker is responsible for expressivity. You have this now it's already kind of common. You have trying to retarget human motion to robot motion, and you probably have a dagger which can kind of distill all these specialist policies into some generalized policies. And with some domain randomization, at this moment, we didn't add any domain randomization. This is the difference. We learn the general tracker. It's just like a learn in the perfect and perfect simulation environments. Well, in the second part, we introduce any adapter, which is the real part handling the disturbances from the real world. So the key is that you leverage a world model to understand how the world will change under different dynamic disturbances and different kind of physical environments. So you try to leverage this kind of dynamic aware embedding to modulate your policy in a film-like setup and still introduce the randomization in the environment so that the adapter is indeed kind of reactive to different kind of disturbances. So with pretty much similar philosophy to RMA, this kind of pretty common works. But the difference is you want to make sure the dynamic embedding really reflects the word kind of properties. And at the same time, it's modulating the anti-tracker in a more kind of effective ways. So as a result, you can see now the robots can just like do very vivid behaviors, expressive behaviors in real worlds, different terrains, different motions, all with a single kind of tracker. While at the same time, you also probably see this very vivid animation, very vivid videos before. So people just try to kind of hit the robots, but the robots can be super robust to the terrain and also these external disturbances, okay? Okay, so this is what executable diverse motion really looks like. So it's indeed executable and robust enough, and at the same time diverse to cover various of human-like motions. Now I want to ask a harder question. Once you have a tracker that can track diverse motions, the natural thing is, does this really scale up, right? Does motion tracking skills like language? We have already see a lot of LLMs, with GPT style learning, you can easily kind of master a lot of knowledge from different corpus. But now, can we just throw more data, throw more human motion, tries to make sure our tracker is also a very general and broad human behavior prior. So this is the question we asked in the second piece of the work. Here is the short answer, which is definitely yes, right? So, but not only because the motions are executable, but also because we're trying to scale up the kind of motion corpus in a meaningful way. So now we systematically consider this scaling problem from three aspects, from data, from model, and also from the experts aspect. We tries to kind of scale up the previous humanoid motion tracker with more than 2 billion frames and 300 clusters for expert trackers, and also a larger model with more than 80 million model parameters. We leverage some causal transformers similar to GPT, and we still leverage the dagger distillation. Seems a simple strategy, but it helps us to scale up the motion prior to establish a broader behavioral prior for robots. So this is the work just presented last month at CVPR. It's called Humanoid GPT, okay? So the key thing is diversity is the most important thing, not just volume. It's not just because we have more than 2 billion frames, but really how we make sure the data set well kind of covering all kinds of diverse human behaviors. That's the secret behind this kind of scaling. So we started from some existing motion data sets, and then we analyzed their drawbacks, no matter whether they are kind of noisy or because the diversity is not enough. We just add carefully curated data from different sources and also from our own mocap studios. And in the end, we can constitute this very diverse data sets, which can help us to learn a general humanoid tracker. So as we expected, the scaling curve naturally kind of comes out. If you increase the amount of the data, the tracking error will decrease with the data. And also using a more scalable architecture help us to learn this kind of scaling behaviors easily. So this is the first time to our knowledge that we have observed very clear scaling behaviors in a humanoid motion tracking foundation model, okay? So the downstream effect is as expected. So basically zero-shot behaviors. We want to check some motions we have never trained or never observed before. This could include contact-rich behaviors with the floor or some balancing behaviors as you observed here, okay? So they're not just cherry-pick examples. They're zero-shot behaviors. This also demonstrates the system indeed generalizes to live human motions. If you like allow the mocap behaviors to arbitrarily move, you see the robots just tracking the behaviors reliably. So we have already open sourced the checkpoint and also the evaluation code, which can help. You can also try that on your own Unitree robots. So we also do a side-by-side comparison with the contemporary work Sonic. Yeah, it's a pretty strong contemporary work. So yeah, I won't explain much. You can just let the video tells how like humanoid GPT could perform a more expressive motion as demonstrated here. Okay. Okay, let me now return to the organizing equations. We have now built the first term, broad executable behaviors. Okay, the robot has support over a huge space of human-like motions. So now it can execute them robustly in the real world. But here is the limitation. We have to be honest. Like support is not really choice. If you want to execute or achieve certain tasks, it's not just like you have broad motion support. That's not sufficient. Okay, so what motion you have to leverage in order to achieve certain tasks? That's the tricky part. So for that, we need the second term, which is structure deviations. So to make this concrete, we pick up a pretty hard task, humanoid tennis. So now a robot on a real court against a real human opponent.
The audio?
Audio. Probably I mute the, I don't think the audio is useful, okay? You can just like, yeah, let the video plays, okay? Um, yeah, this is the first time how a bipedal robot is being to play tennis with a real human player. So why tennis? Because tennis breaks motion priors in a very representative way, right? So the prior robot's needs to play with a human, it's not just like moving like a human. It's how you move your kind of wrist, how you move your arm, how you control the racket so that you can hit the ball and precisely let the ball dropping on the other side of the court. So it's not just like moving naturally like a human can let you win the game, okay? So that's why we have to think about how the robot can achieve the task and going beyond this kind of motion support. The motion prior gives you a rough sense, but it does not give you the answer. So here is the architecture we leverage to achieve for task success. So the human prior, imperfect as it is, will serve as still the foundation, okay? So it will sit at the bottom. Well, now we leverage a high-level policy which tries to select and compose those human-like behaviors so that you can achieve certain tasks. So this is pretty common, right? The prior is not just like the restriction for our behavior. It provides you the search space, while the high-level policy tries to make its own choices to target for task success. Okay, so this is also an incoming work at IROS 2026. It's called Learning Athletic Humanoid Tennis Skills from Imperfect Human Motion Data. Okay, so I want to dwell on this slide because it captures a philosophical commitment that runs through this talk, right? So even if the human motion priors are imperfect, they are still very useful for task success. It helps you to establish this kind of search spaces for kind of tennis plays. It provides you very rich local motion structure, although it doesn't specify what means task complete. Okay. Okay, so here are just some motion data we leverage. We capture human motion, we let them randomly move, and in the studios, they don't even have a racket at all. So I just like capture their running and waving hand motions. Now, these motion priors will serve as a very useful kind of search space for high-level skills. So we need to make sure the skills satisfy three properties. It should be expressive, it should be compact, and also the prior space should be correctable. Otherwise, we cannot really kind of deviate from the space to achieve tasks. So now we just leverage some kind of CBA type of thing to distill the kind of compress these human motions into a latent skill manifold. And when we do this compression, we make sure we only keep the body motions, but just omit the wrist motions, which is pretty important for playing the tennis and make sure you can hit the balls correctly. So this makes the prior space kind of compact while at the same time correctable for high-level policy, high-level tasks. And then this property gives us this kind of expressive, robust, and correctable, and also real-world ready spaces. Now you can just like randomly roll out the motions from that latent space, and then you can see the robot is also kind of running like a real human player, although it doesn't understand how to succeed in this tennis playing. But you can already leverage this behavioral prior and to generate natural running and waving hand motions. The next thing is to kind of learn to search for and compose useful behaviors to accomplish high-level tasks. This is where the high-level policy sits in. So now the high-level policy will just select the latent actions for the whole body control from that CBAE latent space. While at the same time, it will directly control the right wrist motion, right wrist motors with 3 degrees of freedom to make sure you can indeed hit the balls and make the ball running to the other side of the court. So this high-level policy, an important thing is when we are searching and we are deviating from the latent space, you have to make sure you are not deviating too much, right? Previously, there's a human-like behavior space. If you just like search in the whole space without considering the prior support, you can easily generate non-human-like behaviors, which can easily fail the game or generate very weird behaviors you don't like. So we now just leverage this latent action barrier to make sure every time you search for some interesting behaviors and not deviating from the original human structural prior too much. Okay, so you're still searching in the human motion space with certain flexibility to deviate, but the barrier function makes sure you don't deviate too much to break the motion priors. So I think that's pretty important to make sure the pipeline works. And in the end, with a lot of sim to real kind of hacks. And I would say this is engineers, right? You have domain randomization, you have to analyze every single components, carefully do system ID and do the domain randomization with the proper parameters. That's the important thing to make sure the robots really transfer to the real world. Okay, so you have the results. Now the robot just play the tennis with the human player. You can just consider now that the game will just continue running if the human don't purposely breaks the rules. Okay. But here, we're already suffering from SimTree a lot. We're trying to understand how to system ID every component and DR every component. That's not easy for a normal lab to achieve. So that's why it naturally comes to the third question. Let me just return to these slides. Now you have to consider we have the task-directed freedom, but simulation does not fully determine the real world. How can you make sure everything you learn in the simulator still transfer to the real environments? How can you close the sim and real gaps? So to answer this question, I think people has been studying that for a while, for a long time, but still we didn't get the perfect answer. So in our lab, we try to study, so how can we do a little bit better? So this brings me to the third term and third work. So here, instead of humanoids, I choose to use this kind of dexterous manipulation as an example because this is where the reality gap is the worst. So you have a lot of contact, right? And also a lot of like motors. Again, the dexterous hand rotating some objects, the contact dynamics, the frictions, the finger compliance, none of this are perfectly modeled in the simulator. So how can you make sure you learn something and you transfer to the real world? Okay, so this work called closing the reality gap for dexterous in-hand rotation with John-Wise neurodynamics model is also from our lab and just presented in the past iClear 2026. So the mathematical statement for this problem is that the simulator's dynamics function is not equal to the real world's dynamic function. So the same action would produce different state transitions both from the same and from the real world. If we want the simulator trained policies to work in reality, we have to close this gap, not kind of statistically from randomization, but maybe explicitly through some real-world aware models. So how to achieve this? So the classical approach is to learn a neural dynamic model from real-world behaviors. So just collect a lot of real-world trajectories and you train a neural network to predict the next state from the current state and actions and use it to train or correct the simulator learning policies. So this has been this is like a working solution in some domains, for example, quadrupedal robots. But in more complex domains, like those contact-rich dexterous manipulations, is even more challenging. Okay, so our key insight is now in this more challenging multi-finger dexterous hand manipulations, we don't just model the whole hand degree of freedom at once. We try to model every single joint's degrees of freedom separately. Each joint will have its own local dynamics, its own position, velocity, and the action is received, and then it will predict its own state. So the difference is that if you learn the whole hand dynamics in the super high degree of freedom state and action space, you will find the learning this problem is very challenging. You collect some data and it's easily to deviate from this space. Well, if you now boils down to this joint-wide dynamics, you are faced with a much lower dimensional space, and it can easily generalize and transfer to new kind of observation and action things. You might kind of worried, is this joint-wise neurodynamics model as expressive as the whole hand dynamics model since the state and also the action dimensionality has been reduced? So from our experiments, yes, it's still as expressive as the whole hand dynamics model. This might think interesting or strange at the first hand, but after examining carefully, you will find that from the proprioceptive history of every single joint and also its own actions, it's actually possible for every joint to kind of hallucinate the context information for the whole hands and also for the objects. That's why learning a joint-wise neurodynamics model is still feasible in this setup. And also it makes the data collection part easier. Instead of collecting those in-hand rotation behaviors and directly learn those whole hand dynamics, you can use a much simpler kind of setup, which is a hand rotating in a chaos box. And you just collect a lot of data, learn this neurodynamics model. We find that this joint-wise neurodynamics model allows easier generalizability, okay, across different behaviors and across different tasks. So this is a t-SNE visualization. The red dots, the blue dots, they just represent different behaviors from the data collection and from the real execution. And also from sim and from the real world. You will find like the joint-wide dynamics, the sim, the collected data and the real task relevant data, they're nicely aligned. But if you collect data in the chaos box, which is not really in-hand rotation, you will easily observe the whole hand dynamics differ dramatically from the in-hand rotation behaviors. So with this kind of neurodynamics model, you now can just learn to compensate the original kind of policies. In this case, we are considering in-hand rotation as a surrogate task. And you just learn some residual policy to compensate this in-hand rotation thing. And now you can just keep rotating arbitrary object and challenging objects. For the first time, you see very cheaply can rotate super huge books like that, and also long cuboids and very, very tiny and very kind of sophisticated geometry, as you can see here. And we just compare this paradigm with previous works like Rotate and Visual Dexterity. They're very nice works published before. You will find now with the better sim-to-real recipe, you can cover more challenging cases, right? Just down-facing, rotating very challenging objects, okay? So this is how we go beyond just domain randomization and standard system identification. And finally, the recent work just brings us brings this philosophy to back to humanoid motion tracking. So in this case, we try to leverage the similar philosophy, and we want the humanoids to understand the real world dynamics from its real world behaviors. So this is an interesting example. We use a common unit tree to track some motion. You will see now the unit tree will just like do this kind of bow motion. And on the left-hand side, it's actually a robot has been used for a long time, and the motor behaviors has been out of control. So if you just track the similar motion, you will find due to the hardware gap, the behavior looks so weird. But it's okay. We just let the robot to do motions in the real world and trying to collect data from the real executions. And these real world experiences allows the robots to establish some neurodynamics models. So this neurodynamics model can help you to close the sim-to-real gap, because to be honest, we don't really understand how to model these motor behaviors in a simulator after it's been used for so long. And after the robots collecting all this real world data for roughly 20 minutes, I think, yeah, it will finally come to the end of this video. We just like speed up. It's 20 minutes robots playing in the real world. You have to make sure the robots are not falling down, because we don't want human to get intervention and the robots has to stay safely explore, well, not still explore much so that you can establish those dynamic models. So now you see the robots just do the bow motions as nicely as you expected. So this is how the neurodynamics model help us to close the sim-to-real gap. And also it's an important thing to let the robots continuously learn after it has been trained, and continuously collecting data from the real world and continuously improving and calibrating its own behaviors. So this is another example. We want the robots to walk a straight line. So this is the normal case. But now if you try to equip the robots with some heavy load, you will see the robot cannot work a straight line as expected, okay? Yeah, so due to the system, and also it's very challenging because the bottle contains water, so we don't know how to model that in the simulator. So again, we just let the robot to explore in the real world, collect data. I will directly jump to the end of the video. Oh, it's too much. Okay, so now you will see the robot can now walk a straight line after collecting its own experiences for long, okay? So let me close the loop and visit the equations again. So each term restated as a lesson. So the first question tells us priors should be designed for correction, not just imitation. You should make sure it's executable and robust. And the second part, skill, will emerge from structure deviation, not just data skill alone. You have to make sure you understand how to deviate from human priors in a controlled way. And finally, sim-to-real is a model design problem before it becomes some data problem or engineering problem. And finally, let me end with 4 claims I believe may be true. And first, the humanoid skill problem is bottlenecked by interfaces, not just data. Today, I talk about 3 different interfaces, from human to robot, from prior to task, from sim to real. It's not just adding more data can make these things happen, okay? You have to care about the interfaces. Every interface, they admit some sort of decoupling. We found some, right, decouple expressivity from robustness, decouple prior from task success and decouple joint-wise dynamics from the whole body dynamics. I believe there will be more. So the next question is whether the robots can discover when they can deviate from these priors and when where the priors should be stiff and where the priors should be elastic with their own experiences, not just like manual designs. And I think a big bottleneck is contact rather than motion. And our dynamics model are not ready, so there will be a lot of hard problems being explored to be explored in this contact-rich whole body manipulations. Okay, that will just conclude my talk. Thanks, everyone. Thank you for the question. Yes, please.
Yeah, I thank you very much for the great talk. My question is that what if we don't have a prior? Let's say because before 2022, for example, in robotics field, we like to create skills. We design handicraft controllers, planners. What if we don't have the prior human motion prior?
Yeah, from my perspective, it's just like you are adding priors at different stages, right? For example, previously we handcraft everything. That's also kind of prior, right? We just use our expertise knowledge to design what we think is correct. And maybe the search space for motion planning, maybe the model for the control, okay? Right, so this kind of thing is from physics, from our human knowledge. There's also some instantiation of the priors. So now it's just like a cheaper way to get the priors and also a more scalable way to get the priors by leveraging or looking at human motions. Yeah, it's just like changing the format of priors from my perspective.
Yes, please.
So I found like the pennies and like at the second last of the slide, like it's walking with the chart with a hand, like some kind of looks like a long horizon planning you're solving. Like you might be having some failures, like how are you executing them in closed loop or open loop fashion? And I found like it seems to be like you are combining multiple skills together. And are you using some kind of a value function to combine at which particular time step I will trigger which skill? Yeah, these are questions.
Yeah, that's a nice question. So for this kind of long horizon stuff, if you choose to leverage RL, now designing reward is also another way to inject human knowledge, right? So how can you, maybe you want to decompose the long horizon thing into several phases, and you have different rewards, which can maybe switching between different phases. Yeah, that's something kind of we have to develop at this moment, but we believe in the near future, maybe you can just leverage some agentic frameworks to help you to automate that process to leverage to make the long horizon planning or long horizon reward design easier.
Yeah, please.
Yeah, my question is the simulation retargeting the only way to transfer the useful real-world human behavior into the robotics that we consider about? So the question is rooted from the observation that if you're doing retargeting in simulation, there are a lot of information losing, like the object you are interacting with or the open world scenario, open world visuals that can be formulated in the simulation. So I was wondering, doing the simulation retargeting, would that be the only way that we transfer the human knowledge?
Yeah, that's a very nice question. I'm also thinking about that. I think one way will be scalable real to sim. So if you have a way to kind of convert observations into sim-ready environments, you probably can incorporate more tasks. But I agree, simulation has its own limitations. You cannot just model every physical phenomenon in the simulator at this moment. Yeah, improving simulator is also another direction. And in the end, people will consider leveraging teleoperation, real-world behaviors, and learn directly and transfer to similar embodiment robots. In the end, I bet you will probably have to leverage all the stuff in a kind of joint recipe somehow.
All right. Thank you, Lee.
Thank you.
Let's thank the speaker again.